Center at Darmstadt in Germany. I'm in the center of the main complex in reception, which was actually an awful lot busier here a few moments ago, as hundreds of guests from all over the world streamed in to witness with me one of the greatest space encounters of International Space Year 1992. The encounter between a comet and the probe which went to see Halley's Comet back in 1986, a close encounter of the second kind. This program's coming to you in English, even though we're coming out of Germany, because that's the common language used here by the engineers and scientists who work here controlling the probe and looking for the comet. The engineers are in mission control over in that building over there. They're making sure the probe is targeted right into the heart of the comet, and the data goes to the scientists in there. Many scientists from many European member states who are getting together to bring you some very exciting news this afternoon. Well, as you can imagine, it's action now. It's really crowded in both mission control and the scientists' headquarters. So what we've done is to organize that this whole program and all the data that comes and all the exciting scientific discoveries from Comet are coming to you in another room. And this room is packed with dignitaries, as I hinted, from all over the world, including heads from NASA and also from Russia. So it's a fully international jamboree going on here this afternoon. And of course, some young scientists whose careers actually started off with Halley's Comet back in 1986. And as I walk into the room, I can't help to tell you the thing that really zaps you in the face. Thank you. Thank you, everybody. The thing that really zaps you in the face is the full-scale mock-up over there of our space probe. That's our hero for today, by the way. It was built for especially by British Aerospace in Bristol in collaboration with Dornier in Germany. But our story starts at a conference in Padua in Italy in 1981, when they gave the space probe its name. They called it Giotto.
The name comes from a painting by the Italian Giotto di Bondone, who saw Halley's Comet in 1301. Compare that with the view from Earth in 1910. Seen from the ground, its return in 1986 was disappointing, but the Giotto mission to Halley's Comet produced spectacular discoveries. The spacecraft was damaged, but not destroyed. As it flew away from Halley, it was preserved in hibernation until a decision was taken on what to do with it next. 4 years later, as it came back towards Earth, it was reawakened and sent to its second target. First identified by New Zealander John Grigg in 1902, then a few orbits later from South Africa by Frank Sjkellerup, their faint comet without a tail promises to be very different from Halley.
Today's target, Commet Grigg Sjkellerup, that's our second hero. Giotto will cross its orbit, as you can see, in about an hour's time, and it's still 56,338 ticking down kilometers out. And the Earth is in this picture too. It's the little dot you can see right in the center of your screen, 214 million kilometers away from all the action. Well, we can bring the action to you here with the help of Professor Johannes Geiss, who is probably one of Europe's most distinguished scientists who succeeded in getting cometary research actually off the ground and out into space. Johannes, I needn't tell you, you've participated in more than 20 space missions, including the Apollo missions, and of course you were very active in the Halley mission that Giotto was on 6 years ago. Why are you so fascinated by comets?
Comets are interesting, particularly interesting because they contain pristine material. That is to say, material which was not altered since the origin of the solar system 4.5 billion years ago. And by going there and probing a cometary coma, we can measure the contents, the composition, what molecules, what the dust made of these comets, and that tells us a lot about the origin of the solar system, but also of the origin of our Earth.
And life itself, perhaps. But why do we want to go to a second comet since we've done old Halley?
Well, you know, Halley is a very big comet, as we have seen in these wonderful pictures. And we expect that Grigg Sjkellerup is very small and also much less active. Now, that doesn't mean it's less interesting, because we like to compare a big and a small comet, because the physical processes, the chemistry, is rather different.
Sure.
And therefore, we have to have this comparison to understand better what's going on inside and around comets.
Well, as we all know, a comet is really all show. The dust and gas that you refer to form an enormous head, the coma. In this case, it's 60,000 kilometers across. But it all comes from a dark, mysterious nucleus hidden deep inside.
The Grigg Sjkellerup nucleus could be anything from only a few hundred meters up to nearly 2 kilometers across. But compared to Halley's nucleus, it must be very small. For that, in 1986, the scientists had 10 instruments aboard Giotto. The multicolored camera produced an image, but in contour maps of false colors, difficult for laymen to understand. But now they've been converted into a sequence of astonishing beauty.
Those pictures were beamed back to Earth from Giotto's high-gain antenna. Until something dramatic happened.
Transmission back to Earth was lost. The pictures disappeared. To viewers watching this on television, that looked like failure, and even the controllers were shaken.
Giotto, travelling at 50 times the speed of a bullet, had hit something the size of a dried pea. At that speed, it was like being hit by a hand grenade. Now, the bad news is that it smashed into the camera that took those pictures. And that means on today's encounter, there will be no new pictures. Giotto is blind. But it's far from helpless. Although it's handicapped, the battered, limping probe can sense its environment very well. In fact, after the bash with the particle from Halley, Giotto was back in business after just 20 seconds, collecting data with 8 out of 10 of its other instruments. And after 6 years, those instruments are now on their way to Grigg Sjkellerup. Now, you've said that Grigg Sjkellerup's a much less active comet than Halley, so surely there's no risk this time.
I wouldn't say that. There is, in fact, much less dust as we anticipated. The dust is also slower, so this makes for more safety. But, however, Giotto has a different approach this time, in a way. Instead of going with these dust shields into the forward direction, into the cometary dust, it has to go sideways to keep the transmission to the Earth. And therefore, most of the dust will hit the sides, hit the instruments, and in particular, the solar cells.
So they could be degraded?
They could be degraded.
Well, let's go over to where they're watching over the health and safety of Giotto in the control room. And we should have with us Manfred Grenzemann. In fact, at the moment, the spacecraft operations manager is Antonello Morani, but he's concentrating very hard on what happens to the spacecraft. So I'll talk to Manfred, because Manfred's been the project manager for the last 3 years. Manfred, why send a damaged space probe into a comet?
Well, the spacecraft was not so much damaged as we had expected when it would pass Comet Halley. It survived remarkably well, and when we did the first check after the Halley encounter, we found that several experiments were still working. Of course, the time was at that time too short to make a detailed assessment. So in 1990, we reactivated the spacecraft, and then we checked the spacecraft and the experiments out in detail and found that we could fly with the payload and with the spacecraft a second mission.
Fine. Well, as the flight operations manager who controls, this is Howard Nye, who I can see sitting next to you. Hello, Howard. You look very busy. But how far away is the comet, and is this going to prove difficult for distances?
Well, the spacecraft is 214 million kilometers away from us at the moment. And this means that if we send messages to the spacecraft, it takes 12 minutes to get there and 12 minutes to get back.
Well, what if something actually happened? You'd lose your data.
Well, we have a series of contingency plans already here, and depending on what we see, if anything goes wrong, then we go straight into semi-automatic mode to take over contingency actions.
So essentially it's on its own. There's no way the control center can reach it within 24 minutes. In fact, at the moment, talking of the timings, we have a time to closest approach at the moment of 1 minute 1:08. Is that time at the comet, or is that time here?
That's the time on the ground. Of course, the encounter occurs 12 minutes before that in space, but we don't see it until the data gets to us on the ground.
So that's the Earth time. Well, let's stick with the Earth time, because that's when the signal reaches. That's what it's all about. Thank you, Howard, and I will be coming back to you later, often, little and often, we hope. Thank you very much. Well, whatever data comes back from the control center where they're flying the space probe, as you know so very well, Johannes, goes to the scientists. Let's take a look at the video bank and see what the scientists are up to at the moment. Have you had any news?
Yes, it's very good to tell that, of course, as we are approaching the comet, some experiments have definitely detected cometary material.
Yeah.
That is water which has been disintegrating. So we are sensing the comet.
Well, let's go and sense the comet over here. As you can see, just next to the model of Giotto, we have something which I think to some of you in the room who are not scientists will look like a kind of glorified cosmic jellyfish, but I assure you it's not. And I'm going to get Johannes to explain really what this model is meant to be showing you. This is our own Grigg Sjkellerup for the afternoon.
Well, inside here is the nucleus, a solid body emitting gas and dust because it's heated by the sun. And this gas expands, and then it's driven by the solar wind, which is coming this way in this picture.
That's a bit like the sun's hot breath, if you like.
That's right, yes. And formed into the tail. That's like if you have a chimney, smoke coming out, and the wind just carried it away. And
just here, where you have this, if you like, the comet's surface between the solar wind and the comet's gas, that's the bow shock, isn't it?
That's the bow shock. But we are, of course, outside it, but still there's cometary gases coming outside, and we sense it, and several instruments have seen it already.
So they're leaking out right outside the comet.
Right.
Well, let's go back to the video wall, because I can actually see one of our colleagues on the screen at the moment. That looks like Fritz Neubauer over there. And I might just ask him, Fritz, are you hearing me?
Yes, I do.
You are jolly good. I'll hand you over to Johannes in a moment, but your experiment essentially senses the environment of the comet. Anything you're picking up?
Well, we have the first indication of some weak waves, but they seem to be clearly of cometary origin. In fact, that's about half an hour earlier than we expected this.
What does that mean for you?
Well, one thing is, or one reason probably is that the solar wind is relatively quiet. So the background where we have to distinguish against is very low, so the situation for the detection of these waves is reasonably good.
What wavelengths do you have?
Well, the wavelengths are, I would estimate, a few thousand kilometers.
Goodness me. So if you could hear them, it would be a very low note. Johannes, I understand that Alan Johnston is wanting to talk to you over there at the moment.
Good. Yes.
So while we get to him, it looks very, you see what I mean about it being crowded in there? It really is. And Alan's in the corner over there. Alan is in charge of the Johnson plasma analyzer. He has his own experiment named after him. And I think he can pick you up now, Johannes.
Yes, Alan, can you show us some pictures how you really see the cometary ions?
Yes, we're showing them now on your monitor. We first detected the pickup ions from the comet about 5 hours ago, when it was still 300,000 kilometers from the nucleus. And since then, the density of the ions has been steadily increasing, and we're now getting some very interesting distributions, which you can see here on the screen, which are very typical of the cometary ion distributions that we expect. So it's behaving just as we anticipated the distributions would, and I think the density is building up nicely so that we're going to get some very dynamic effects before very long.
That's very exciting. Shall we go on to talk to somebody else, just so we don't disturb Alan too much at the moment? We have Susan McKenna-Lawler in the corner. Many of you who saw the previous Encounter programme might remember Susan as the lady in the red hat. Now I see she has changed into a very attractive purple outfit and having her headpiece put on at the moment so she can hear me. Susan, are you hearing me loud and clear?
Indeed I am. Hello, Heather.
Hello, Susan. Let me just first of all ask you about the name of your experiment, EPONA. What does it mean?
Well, it's an acronym for what the experiment does. It stands for Energetic Particle Onset at Monitor, but it's also the name of a Celtic goddess who's associated with the commencement of the solar year. And if you turn your camera up above our place, you will see the Celtic goddess riding out to bring data back from the comet.
Well, good luck, Susan. That sounds very auspicious indeed. Again, we'll be talking to all these people later on.
An opportunity to see again the events first shown live on Discovery in July 1992.
It's now less than 30 minutes to closest approach. It's getting very exciting in here. As you can see, it's just over 30:49. We have very, very short distance to go. Johannes, I've been busy for the last few minutes, but have you heard of any data coming in? I noticed actually on my television set, I can see Gerhard Schwemm, who is the scientist in charge of operations today. Gerhard, how's it going?
Yeah, it's going very well, and you see it's getting really exciting now, just this half an hour before the closest approach. I have already left my chair to see the exciting data, and I moved to Fritz Neubauer with the magnetometer experiment, and he will explain you what he has seen.
Over to you, Johannes.
Fritz,
Yes.
I understand you have a lot of waves. Maybe you show us how they look on your paper.
Yes, we have some very interesting waves here.
Oh, we can see them
very
very
well
well.
developed, clear and periodic waves. And you can best appreciate them by comparing them with the data of the quiet solar wind, which essentially shows nothing or very small
It's
activity.
a spectacular difference, yeah.
Here you have really these strongly nonlinear already, with also superimposed high-frequency waves, which are probably due to some complicated interactions.
But when you say high frequency, they're still very long wavelengths.
Yes, there are, again, these several thousand kilometer wavelengths, and
they are produced by the picking up of water into the solar wind stream.
Yes, they are produced by the ions, produced by ionization of cometary material, and the free energy of these particles is then going into the generation of these waves, like in some, let's say, traveling wave tubes or so. In electric engineering.
Right, that's fantastic. Fritz, thank you very much. Can we come back to your waves later on? I did hear in my headphone, I don't know if anyone can confirm it, that was just, it wasn't, you're not actually catching dust. Okay, that would be very exciting.
Yes, but we should talk now to Henri Rem. I think he has good news.
Yes, as you can see on the screen, we obtain with the electrons very clear waves with a period of about 1 minute. And these waves are really very well correlated with the magnetic field variations.
Well, that's fantastic. I think that's better than you had expected at this time, huh?
Yeah, we expected to have some waves between 50,000 and 30,000 kilometers.
So this comet produces a lot of waves.
A lot, much many waves than in Halley's Comet.
That's amazing. Can we actually go back to Halley's Comet for the moment? Because I find it remarkable that so many of the instruments are still working. In fact, for what some people thought was a kamikaze mission to Halley's Comet 6 years ago, we do seem to have virtually everything still up and running. And what happened to Giotto during those 6 years, and how the European Space Agency's engineers and scientists got it here, is a remarkable story in its own right. Let's pick it up at the point where Giotto was hit by something like this.
But as it turned out, on some of the scientific instruments, data was lost for only 20 seconds. And more was obtained as the spacecraft flew out of Halley's Comet. A few hours later, when some were ready to turn it off, the spacecraft was unexpectedly given a reprieve.
We had an enormous amount of fuel left as a reserve, and this was allowed us to make full use of that to choose a target for the future.
It took half the original fuel load to correct its course to get back to Earth in 1990. But as its orbit would take it so much closer to the Sun, this would expose the delicate electronics to its heat. The top must be turned away. But this also loses telemetry back to Earth.
Once the high-gain antenna pointed itself away from the Earth on our instructions, then that's the last we saw of it until 5 years later.
In any case, there were no funds to control and monitor the spacecraft while ESA planned and costed any future mission. Nor had they any further means of checking its condition, or even how that last maneuver had ended. The final instruction had put it into hibernation.
Well, we're 16,872 kilometers from the comet, and there's 20 minutes to go. And we've just picked up news from the scientists that Chantal Levezé-Rigaud over there has picked up some interesting details with her OPE experiment. Johannes, over to you.
Did you really detect some dust already, Chantal?
Well, in fact, not yet dust, but already gas. For 10 minutes, we have already been flying inside the gas coma, and we see it very well from the CO+ data. So that's quite exciting. We are really in the comet.
So there's carbon monoxide there.
Yeah, still quite
very interesting.
Chantal, do you reckon you're inside the bow shock?
Well, no, we can't. From the preliminary data we have, but we'll find something later. But obviously, we have the data to find it.
Right, okay. Let's go and talk to Tony and see if he's picking up anything at the moment, just to see if I can confirm the rumor in my headphones about, 20 minutes ago that there was dust. I still don't know. It was about bow shocks instead, okay. And I wonder if Alan Johnston is picking up anything at all with his pickup irons. It is, fine, we have Alan Johnston now. You meant Alan rather than Tony, didn't you? Yes, absolutely. Alan.
Yes, well, the news is we're just crossing the bow shock at a distance of about 15 to 18,000 kilometers from the nucleus, and it's a much cleaner and much more well-defined bow shock than we ever expected to find here. So if I show on the plot here, you can see that the density is suddenly shooting way up, and the velocity is now starting to go right down. And if we look on the other displays on the next one, we can see that the distributions have broadened right out, so that they've got a lot hotter, and that is a very good sign that there is a proper shock wave there. So we're finding this particular piece of transition here is one of the most interesting that we've ever seen, I think.
Very good. And it's further out than was anticipated, huh?
Yes, it's about 3 times further out than we had expected from this morning's measurements.
Does that mean there's more gas? Or?
Well, there does seem to be more gas here, yes. The gas that we're seeing here now is much more dense than we would have expected on this morning's measurements. But one of the reasons for that could be that the comet has brightened up in the last few days.
Alan, can we come back to you later on that? Because it is thrilling. It's just that I have to say that after Giotto came out of hibernation 2 years ago, the combination like yours of instruments for studying the plasma was a major factor in the decision to carry on with the mission. And in fact, scientists whose instruments no longer worked were actually amongst those who wanted it to go on. In fact, it would be much cheaper than a mission for which a spacecraft had to be built and tested and launched. And in the end, the European Space Agency didn't have to go through the diplomatic nightmare of trying to collect new money from all the member states. As Giotto headed serenely towards the Earth, they had the decision, the funding, and the target. What they needed next was a sharp change of direction to reach it. This will be another first for Giotto.
For their course change, they planned to fly so close to the Earth that its gravitational attraction would swing it into a completely different orbit, farther out from the Sun.
If we had made this same correction using fuel alone, we would have needed 50 times as much fuel as Giotto was then carrying.
July the 2nd, 1990, 5 years to the day after launch, and 23,000 kilometers over Australia.
And in Australia at the time, it was night, and we were hoping that astronomers would be able to see a pinpoint of light. We were also hoping that it would be picked up by radar, but in the end, nobody saw Giotto flying past the Earth.
No reports.
No reports, only negative ones.
The next stage of Giotto's journey required a much improved diagnosis of the damage to its thermal insulation. It was clear that on its new orbit, further from the Sun, Giotto would get very cold. Could it survive this new peril? Its batteries had been designed to last only through the Halley mission, and the only source of power on the spacecraft is the solar panels. These had survived Halley, but now, much further out, they would no longer provide enough power for continuous operation. So, once again, Giotto was put into hibernation. This time, there was no choice. Meanwhile, its intended target, Commet Grigg Sjkellerup, was also out of sight, on its way back from somewhere near the orbit of Jupiter. It approaches the Earth's orbit every 5 years, and last time, in 1987, from Calle Alto in southern Spain, their big telescope took a picture of it when it was near its closest to the Sun.
Oh, that's a picture of the comet showing an extended coma of about 150,000 kilometers diameter. It doesn't develop a tail, but this seems quite interesting for this extended Giotto mission to have 2 different comets. First, the Halley, very prominent, very bright, and now this faint object. Hopefully one can learn more about the inner part of the coma. of a comet which has less activity than Halley.
Because even then Grigg Sjkellerup was on the list of Giotto's potential future targets, the telescope tracked it across the sky so its orbit could be checked before it disappeared. In August 1991, they searched for it again by pointing the telescope and slowly moving it along the calculated path as they built up an exposure. It's quite difficult to spot.
Here, right here, you can see the comet. This tiny dot, a very faint image still at the moment of the recovery.
But easier to see on the printout. On a time exposure, the surrounding stars trail across the picture. Right in the middle is the comet, exactly where it should be. From now on, the orbit of the comet would be checked and recalculated time and time again.
Well, we can do better than that, because with us here, we actually have the latest photograph of the comet. Can you show us, Johannes?
Yes, this is a photograph of Grigg Sjkellerup, was really taken this morning.
Right.
At the Chile Observatory of ESO, and there's Klaus Jockers from the Max Planck Institute at Lindau, and he kindly somehow transmitted it to us.
Well, that's marvellous news. And in fact, as Alan Johnston was saying, it appears to be a little bit brighter than it was.
And of course, it's very valuable to compare the optical picture with the data we are getting.
Yes, indeed. Well, that's a marvellous picture, even though it's, in astronomical terms, 14th magnitude, which is a very, very faint magnitude indeed. Let's go back to problems with Giotto. There aren't any problems with Giotto. In fact, as I can see from the wall, it's only about 10,000 kilometres now from the comet, and it's closing fast. And so it's doing a really excellent job. Now we can see the reason for the main hazard, though still faced today by Giotto. It's what's called its orientation. Although it's still a long way out from the sun, and so to get power, the solar cell's angled flat onto it, and the high-gain antenna has to point back towards the Earth, which means it has to go into the second comet at a very, very awkward angle. Let me show you what I mean by moving across to the model of Giotto over here. And I must say that if we actually were at the real Giotto, this, of course, as you know, is the model, I bet it wouldn't look anything like as glorious and pristine like this. It would look like a car that had actually gone in, a second-hand car that had got into a crash, covered in dust and stuff. As you know, in the first case of Giotto, it was designed to fly into Halley's comet, bumper shield first, and even then it was damaged. This time, the comet is actually flying in like this. So the instruments and solar cells are no longer protected as they were in 1986. In fact, if it goes in like this, the dust is actually going to hit them straight on, and it will get in here to the second layer of the bumper shield. So this is where Giotto is now, closing in very, very fast. And if you were actually inside the comet, looking out towards Giotto, this is the angle you'd see. There it is just here. Dust goes straight in from that side. And that's exactly what we'll see as it happens for real. And there it is. And I can see Tony over in the scientist headquarters. Tony, are you picking up any dust yet?
No, we just checked the screen. All zeros there, no dust yet, which I think is good news, although it's too early to say we'll be safe.
Well, what I find absolutely fascinating is that you were one of the first guys to pick up data from Halley. And today it's the plasma experiments, if you like, the ones that the public would find less glamorous, which are actually picking up all the exciting data. What do you think of that, Johannes?
Well, it's a different comet.
Yes, that's absolutely true.
You're watching Giotto. Another opportunity to watch the events first shown live on Discovery in July 1992.
Well, it's now 3 minutes and 15 seconds to closest approach, 2,700 kilometers to go. It's like one of those planes you travel on where it keeps on telling you where you are and when you're going to reach your destination. Except here, remember, we're out in space and we're 214 million kilometers from planet Earth. It's very exciting news indeed. We, I gather, are going over to Susan McKenna-Lawler to see what Epona has picked up. There she's gesticulating. She's gesticulating even before she has her headphones on, so she's obviously finding some interesting data there. I know that the red trace that she detected yesterday was much higher than she was expecting for the number of active particles around the comet. Can she hear us at all?
Hello, Heather. Yes,
Hello
I
there,
can.
Susan. How are you getting on?
Well, I'm rather surprised by what I see here. I have traced, we're plotting omnidirectional counts in channel 1 of our telescope 1, and we're seeing rather dramatic fluctuations there. We have a rise in counts close to the bow shock, and then an oscillating behavior. And I don't know what it means at the moment. We're just recording it.
Do you think you're in what is called the mystery region that was detected at Halley's Comet, where people just couldn't explain what was going on?
Well, there's a mystery region that is rather far out that Henri Rem talks about.
Yes.
There's also the great burst of particles that Epona detected in the cavity near Halley's Comet, but I'm not at all claiming that what I see now has anything to do with that.
We'll let you get back to work, Susan.
All right,
You're obviously doing a grand job in there.
All right.
Yes. We're going across to Tony McDonnell now, who I hope has picked up some dust. If he hasn't, I guess the sweepstake is off, so if you put your bets on it, never mind. Here we are, Tony. Hello, Tony. It's Heather here. Have you picked up any dust yet?
No dust events yet, and it's -2 minutes, so...
It is indeed. It's -1 minute, actually, 1 minute 15 seconds at the moment. Okay. Do you find that very strange, or do you think the particles are much smaller than in the case of Halley's Comet?
Well, we don't really know whether the comet is really turned on or not, really active with regard to dust, although it's been visually much brighter.
Yes, so presumably a comet can give out a great deal of gas, but it has to be rather churned up to start, as it were, getting its surface ablating as well.
Yes, indeed. On Halley, you see, we found that there was a tremendous number of large particles. Now, we are hearing from the optical experiments that there may be some small particles scattering the light,
yes,
but no
we've heard
big
that
ones
from
yet.
Chantal. Okay, well, thank you very much for talking to us. We have 40... Yes, we have a very, very short time now to encounter, as you can see from the countdown on the big screen just there. I hope we don't have the same situation as we had at Halley's Comet when the screen wobbled and went blank. In this case, I don't think we're going to. And what is your feeling about it, Johannes?
Well, in a way, if they're not big dust counts, the chances are pretty good, I guess. But of course, there always can be a single one, you know.
What about gas jets? Could that be a problem coming from the solid nucleus?
Not the gas, but the gas jets take dust along.
Yes.
And the dust is the dangerous thing, you know.
Well, here we... 4, 2, 1, 0. Tony, we're at the comet. We've passed it. Where's your dust?
It's a clean comet.
It's a clean... Yeah. Well, I'm delighted to hear. Obviously, it's a green, environmentally friendly comet that isn't chucking dust all over the universe. So maybe we hope to... Let me go over, if I can, to the flight dynamics people, the engineering...
An event!
Yeah, well, an event!
Yes.
Yes.
We have a dust in.
We had one event. Would you, Tony, can you still hear me?
Yes, indeed. We can publish a flux curve now rather than really very significant.
I would like to suggest that it's probably small number statistics and no one would actually believe you. Presumably, you couldn't even estimate at the moment just how big this event was.
Oh, we could do a lot of statistics in that second event.
Great.
Oh, good. Second event.
Why are you picking up dust when you're actually beyond the nucleus? Does this...
Well, the predictions did actually say that if we're going to look for big ones, there would be big more after the encounter rather than before.
Okay.
But of course, we do have that uncertainty of encounter time. We don't know that yet, really.
Yes. Right, let me backtrack again to all of you viewers who are watching at home and wonder what on earth an event is. I do agree, we haven't explained what we mean. What we mean is that Giotto has been hit by, I think at the moment, is it 2 or 3 particles? That might not sound very exciting, but for a completely dust-free comet, for the Giotto probe to collide with bits, it's very exciting news. It means that as well as all the waves and gas we found pouring off, there really is a solid comet in there with a solid nucleus from which bits of dust are boiling off. And can I come back to control room? How many dust events have we had so far?
It's either 2 or 3.
It's
We're
either
not sure yet, because they may have been too close together.
It's 4 on the display.
In fact, there's a count of 4 possibly. We have to confirm those yet, though.
Fine. Johannes, how do you feel about this?
Yes, it's amazing, but as Tony was saying, we seem to have... There must be some dust.
Yes.
Very fine dust, and rather few bigger particles which he detects.
Yes.
So the grain size distribution, as we call it, the relation between small and big dust may be different from that in Halley.
Is that because Grigg Sjkellerup is a much older comet that's tramped around the solar system many more times than Halley has?
I think this is one of the things we have to find out. If older comets, I think in this respect, what grain size concerns, there are probably many different comets, you know.
Well,
but it could be connected to that, yes.
Well, we've had 4 events so far, and those events actually came post-encounter rather than pre-encounter. Now, is that because Giotto is going into the comet at a different angle from when it was going, as it were, sort of end-on to Halley? What do you think the reason for that is?
Yes, first of all, of course, we don't know the moment of closest distance better than a minute, so maybe it was a little delayed. That would be very interesting if we can find that out. And then, of course, this is statistics. And finally, the emission of dust is not uniform.
Could it well, as you say, it could well be that we actually passed closest approach a minute later when Tony got the maximum of his
Of course, with 4 counts, I wouldn't say that. If you would have 400 counts, you would immediately be able to say that.
Don't tell that to Tony McDonnell. That's what I can say. I understand that Martin Penfold is actually waiting there. Yes, I can see him on the video screen.
Yes.
Johannes, would you like to ask him?
Yes. Have you seen what is technically called the Doppler effect? In other words, some small shift, or have you seen the wobble?
What I can say now, what my colleagues told me from JPL is that we detected a Doppler shift coinciding with the time with the first dust impact, and we have a slight notation.
Yes.
That's what I can tell you now.
So that must have been a big impact, no? The first one.
It might be a very big impact, yeah.
Well, that's...
Thank you, yeah.
It's exciting to think that a comet which has got such low activity can actually produce this kind of effect, and also maybe it tells us we really have gone quite deep into the nucleus or quite deep into the coma of the comet. Have you heard if anybody's picked up the mystery region, which we heard so much about at Halley's comet, the region where there's nothing much going on?
I would guess, but we can ask them, this mystery region, of course, is turned up as Halley, and it may be different in every comet, and it's because it's mystery region, may be difficult to identify so fast, you know.
I think at this point of the programme, we ought to address ourselves to the problem of what's going to happen to Giotto after this encounter, and maybe after we've talked to Tony McDonnell, we can go on to that.
Yes.
Tony, I see you've been wired for sound. Do you have anything to report?
Well, yes, the 4 particles we did detect were very large ones.
Yes.
So there's a lot of mass about, but it just seemed to be in the big ones.
Right. What sort of mass would you estimate, first off?
Well, we're talking about probably 0.5 millimeter for the very biggest one, which might have hit the whole of the spacecraft. Perhaps a little bit smaller than the ones actually hitting our sensors, but quite a big particle, perhaps.
Thank you very much, Tony. I can see that Howard Nye is available in mission control. Howard, I think it is safe to say we have definitely passed Commet Grigg Sjkellerup now. We're out of the woods. And can I ask you, what are the plans to, what are you going to do with Giotto now?
Well, we have a plan which we use on Monday, which is to do a large orbit correction maneuver to take it onto another flyby past the Earth in 1999.
Can't you put the space probe down? Poor little thing.
Well, it seems to be indestructible. It's been past 2 comets, and I think the comets are probably coming off worse for wear than the spacecraft.
I think that's absolutely wonderful news. Do you have enough fuel left for this maneuver?
We have certainly enough fuel to do the orbit maneuver on Monday, and thereafter we'll have very little fuel afterwards. We have to see what we can do with it.
And what do you feel about when it comes back to the Earth in 1999 and makes a swing by? Are there any plans, informal plans, that you might be able to tell me about now?
Yes, we're looking at potential targets, other comets, which would be reachable with the minimum fuel and under the conditions that Giotto has to have in order to meet comets.
That's phenomenally ambitious. I really wish you the very best of luck with that plan. And wouldn't it be wonderful if, like in the 19th century, we had a really great comet coming by at the end of this century that would just put itself right on Giotto's path?
That's right.
Well, let's pray for that one. Thank you very much indeed. What would you think of a plan? It's an amazingly brave and audacious plan to send it to another comet.
It behaves very well, and at the same time there's some surprise, like this one big particle, you know, was as big, probably as the biggest hit by Halley, you know. I suggest we go back to the plasma and fields experiments and make another round, including Hans Balziger's experiment.
Yes, indeed. Well, in fact, what about the comet itself? What about Grigg Sjkellerup? It's an old comet. It's obviously losing matter as it goes around the sun, both gas and dust. How long would you estimate that Grigg Sjkellerup has to exist anymore?
I wouldn't know, but it's not a matter of hundreds of years. It's much longer. But I wouldn't know how long. it will probably go less and less active. But today it was fairly active
it was very,
in terms of gas.
Put on a good show for us. Yeah. I can see that we have Alan Johnston and I can see a finger pointing at a screen, looking very excited. Alan Johnston, are you picking us up there?
Yes, I am.
And what are you finding?
Well, we're starting to see the structure on the outbound leg now. And as far as we can see, it's following the same sort of structure as we found on the inbound. It's too early yet to say whether there will be any strong asymmetries, but again, I think you can see, perhaps from this plot here, that goes through the point of closest approach, that there is a great deal going on. It's a very dynamic situation, and we see in the middle here that the speed of the iron slows way, way down and almost drops off the bottom there. And then it comes up again on the other side.
That was at closest approach. Huh?
That was the moment of closest approach, yes.
So would you say we were rather close to the cavity in this case?
I think we could well have been, but I don't think the data I've got here will be absolutely conclusive on that.
Yes. I understand that all of you are going off this weekend to a retreat where you're going to have a sort of first sort of stab at your data in some secret castle in Germany. Is that right?
Well, some people may be, but unfortunately I can't. I'm heading off for a conference in the US next week.
Oh, dear. Oh, some people have to suffer, Alan, but you've obviously got some good data, so I'm not sorry for you at all.
Yes, we've got some excellent data, and I think the fascinating thing is that it's so different from the data we got at Halley.
It's going to make life much more difficult for all you cometary scientists, though, isn't it?
It'll keep us in business for another few years.
I'm delighted to hear that. Well, what do you think? What sort of comet is this, Johannes? So, generally, what do you think?
It seems to be full of gas and not so much dust, but fine dust. So maybe we should go back to Annie Chantal and see if what she has.
Yes, is Annie Chantal there? Annie Chantal's experiment, of course, looks at the sort of the dust halo, looks at the glow of how...
Yes, it's an optical experiment, so she looks at the whole amount of gas which the light penetrates.
Annie's there. We go to her very quickly. Yeah. Annie, anything to report, but very briefly?
Well, we confirm that the mist distance was certainly smaller than 200, 250 kilometers, and that the closest approach took place a little after 1530 by 1531 and a few seconds.
Thank you very much, Chantal. Anyway, all we've seen and all that's been discovered today will, even though it's amazing, be only another modest step towards what we'd really like to know about comets. Sadly, one future mission to fly alongside a comet and watch and measure how it changes as it approaches the sun was cancelled by NASA earlier this year to save money. But we're still hoping for a future joint mission in which ESA joins once again with NASA that could be even more ambitious. It's called Rosetta.
ESA's Rosetta is designed to land on the nucleus of a comet and collect samples of the crust, minerals, organic materials and ices. It takes a core from beneath the spacecraft, collects some from the surface around it and seals them away in deep freeze for the journey home.
I can see Gerhard on the screen just there, and in fact Gerhard is actually wearing two hats today. There's a great celebration going on in the background there. What are you lot up to? Gerhard, as well as being the project scientist for Grigg Sjkellerup, you're also involved in Rosetta. Why do you want to go and snatch a bit from a comet?
Yeah, I think after we have experienced and really could celebrate this textbook encounter today, the second encounter of Grigg Sjkellerup, now we should go a step further and bring back material from a comet nucleus, that we could do a really detailed, in-depth chemical analysis of the most primitive matter in the solar system. And, you know, we had a lot of scientists here from all over the world, and I think we should take this opportunity really to promote a comet nucleus sample return mission that should be done by all the agencies together to bring this material into the laboratories where we could adjust our instruments to what we will get, and not that we have to develop the instruments 10 years in advance and then we'll get all the nice surprises. I think we really should go for an international collaboration on that and really go to this next step after these wonderful Giotto missions to the comets.
Absolutely, I could agree with you entirely. In fact, talking of international collaboration, I understand that in the audience we have the new administrator for NASA, who is sitting over there with the spotlight on him. Daniel Golden, I'm delighted to meet you, and congratulations on your new post. What do you think of the mission today, and do you want to go and ride on Rosetta?
I'd like to ride on a shuttle.
And so would I. I'll join you there. Thank you very much indeed.
You're welcome.
I also understand that in the audience we have Alek Galayev, who's the director of the Cosmic Research Institute in Moscow. I thought you were over there. You're hiding from me. Okay, fine. And I noticed that you are wearing a Halley's Comet tie.
Comet is unidentified, actually.
It's an unidentified comet. Now, talking of international collaboration, you, I understand, in Russia have a mission coming up next year?
Yes, we have solar terrestrial physics mission,
right?
Interball.
And you also have the Mars mission, I gather, where very many of the scientists from this mission have experiments on board to detect plasma.
Yes, that's true that in our Mars mission we cooperate with a lot of our colleagues from Europe.
That's it. Thank you very much, and good luck with your upcoming missions. It's a very exciting time for space. Well, today's encounter between Giotto and Grigg Sjkellerup has really cast fresh light on all the discoveries that brave little space probe made at Halley's Comet. We can see those findings in a new light. Now we have two comets to compare. You've heard all the scientists talking about that. But this is really just the beginning. There's so much work to be done, both for the scientists working on Giotto's findings and for those who will use the data to plan missions for the future. Johannes, as a scientist who's been involved in so many space missions, what's your verdict on today's exciting goings-on?
Well, first of all, it's obvious it was very successful. I think the Grigg Sjkellerup comet has behaved very well. Was few dust numbers, but still is exciting enough. We got some wobble and so on, so we had to tell something. What was really surprising is how good the data were concerning the dust and the plasma.
I couldn't believe that myself. I hadn't expected them to be so clean.
Yeah, so the experiments worked very well, and at the same time, we have 4 or 5 experiments. We haven't even talked to all of them.
Yes.
The iron mass spectrometer of Hans Balsiger, for instance, has also picked up the water ions.
Oh, now that's exciting, because we've spoken to Hans Balsiger, and I didn't realize he was picking those up.
So there's a lot of confirmation also. The electrons and the ions match and have to be matched. So it's a very great success. I think obviously it was worthwhile to investigate these 2 different comets. And I think, in closing, I would say it's a very good example of a European cooperation.
Indeed it is. And what a memorable event this has been to crown international space here. But it's just the beginning of several exciting projects which include trips to Mars and Jupiter, and even further afield to Saturn's bizarre moon Titan. But for me, the wonderful part of the day was the sheer buzz of a live space encounter and the amazing news that Giotto itself may be going on yet another adventure of its own. But for the moment, it's a temporary farewell to Giotto. We wish you a well-earned hibernation, and good luck to all the scientists here today who'll be going away to work on their results. And now it's time for us all at the European Space Operations Centre in Germany to take our leave of you too. We hope you enjoyed the action as much as we have. From Darmstadt, bon voyage to Giotto, and goodbye.
Hello? It works? It works now?
That was a recording of Giotto, a close encounter of the second kind, first shown live on Discovery in July 1992.